Putrajaya Malaysia and UniKL Malaysia Institute of Aviation Technology. I would like to extend my warm welcome to all guests to the Marriott Hotel Putrajaya, Malaysia. My name is Harijono and I will be the MC for today. So we will start our event this morning with the national anthem. So please accept. Putrajaya. Ladies and gentlemen, you may now be seated. Now to grace our gathering this morning, please welcome Mr. Sapiro Saleh to recite the dua.
Assalamualaikum warahmatullahi wabarakatuh. Ila hadratina Muhammad sallallahu alaihi wasallam wa ala alihi wa sahbihi al-Fatiha. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين الرحمن الرحيم مالك يوم الدين إياك نعبد وإياك نستعين اهدنا الصراط المستقيم صراط الذين أنعمت عليهم غير المغضوب عليهم ولا الضالين أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء والمرسلين وعلى آله وصحبه أجمعين. Ya Allah, ya Tuhan kami yang Maha Pengasih lagi Maha Penyayang, kami menzahirkan kesyukuran kami kerana dengan limpah rahmat dan kurnia-Mu dapat kami berkumpul pada hari ini sempena majlis perasmian Aerotech yang ke-7 bagi tahun 2018. Allahumma ya Rahman ya Rahim, pada hari ini kami memohon kepadamu ya Allah supaya Engkau kurniakan kepada kami jiwa yang mantap, iman yang teguh khususnya kepada kami ya Allah. Allahumma ya Hamidun ya Majid, jadikanlah kami golongan yang bijaksana, berwibawa dan berkemampuan untuk membantu melahirkan masyarakat yang bersatu padu serta saling bekerjasama dalam menjalankan kerja harian kami ya Allah. Tingkatkanlah kami dengan kemahiran dan penguasaan dalam bidang pekerjaan yang kami ceburi. Semoga hasil kerja kami mencapai tahap kualiti yang diterima di peringkat negara maupun antarabangsa ya Allah. Allahumma ya Hayyu ya Qayyum ya Dzal Jalali wal Ikram, kami mohon kepadamu ya Allah, semoga majlis ini lebih diberkati ya Allah. Allahumma inna nas'aluka nas'aluka ahyanana wa anfusana wa ahlana wa auladana wa amwalana kulla shay'in a'taytana. Allahumma jalna wa yumfika nafika wa manika wa yazka min kulli shaytanin marid wa jabbarin anzi wa zi aini wa zi bari wa min syarri kulli syarrin innaka ala kulli shay'in qadir. Allahumma jamina bil afiyati was salamah wa qina bit taqwa istiqamah wa izna min mujibati nadam innaka sami'ud du'a. Rabbana hab lana min azwajina wa dhurriyyatina qurrata a'yun waj'alna lil muttaqina imama. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Wa sallallahu ala sayyidina Muhammadin wa ala alihi wa sahbihi wa sallam. Subhana rabbil izzati amma yasifun, salamun ala mursalin walhamdulillahi rabbil alamin. Sebelum kita bertemu dan berkisahkan Allah insyaAllah. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Safaris, for the recitation. Dr. Fairuz Izzuddin Romli, the Chairman of the Aerotech 7 Organizing Committee, Dr. Professor, Dr. Engineer Insinyur Harijono Djojodihardjo, Deputy Vice Chancellor of Industry and Community Relations, University Putrajaya, Malaysia, Professor Dr. Nur Kamaria Nordin, Dean of the Faculty of Engineering, University Putrajaya, Malaysia, Mr. Muhammad Iqbal bin Muhammad Ali, Deputy Dean, Academic and Technology, University Kuala Lumpur, Malaysian Institute of Aviation Technology. Honorable speakers, ladies and gentlemen, Assalamu alaikum and welcome to Aerotech 7 2008 Sustainability in Aerospace Engineering and Technology. Aerotech 7 is an international conference which aims to promote advancement and innovation in aerospace engineering and technology. It is a platform for academia, government agencies and industries to share the current status and issues in aerospace research and to expand professional networkings globally. We would like to welcome you and offer our deepest thanks to all for joining us here at this 7th installment of the Aerotech Conference in Putrajaya Marriott Hotel, Kuala, Malaysia. Distinguished guests, ladies and gentlemen, we will start this conference with a welcoming speech from the Chairman, Dr. Fairuz Izzuddin Romli. This will be followed by a speech from the Deputy Vice Chancellor of Industry and Community Relations, Professor Dr. Engineer Insinyur Harijono Djojodihardjo, and to officiate this event. And this will be followed by two keynote address of Aerotech 7. First by Professor Dr. Harijono Djojodihardjo, Chairman of the Institute for the Advancement of Aerospace Science and Technology, Jakarta, Indonesia, with the title, The Vision for Solar Radiation, Magnetic and Electric Sailing for Interplanetary Missions. And secondly, by Associate Professor Dr. Mohammad Fard from the Royal Melbourne Institute of Technology, Australia, with the title Concept Modeling Method by Optimization of Complex Structures. And for your information, we also have a morning break between the keynote session and the parallel presentation sessions, which should start at 11:30. Distinguished guests, ladies and gentlemen, now to start our conference, the stage now invites Dr. Fairuz Izzuddin Romli, Chairman of Aerotech 7, to give his welcoming remarks. So please welcome on stage.
Assalamualaikum and a very good morning. Our distinguished guests, Prof. Dato' Dr. Engineer Putrajaya, Deputy Vice Chancellor of University Putrajaya Malaysia, Professor Dr. Nurkamarian Nordin, Dean of Faculty of Engineering, University Putrajaya Malaysia, Mr. Muhammad Muhammad Ali, Deputy Dean of Academic, University Kuala Lumpur, Malaysia Institute of Aviation Technology. Our invited keynote speakers, Professor Dr. Harijono Djojodihardjo, and also Associate Professor Dr. Mohammad Fard, and all conference participants today at this Aerotech 7. So welcome. First of all, I would like to thank all organizing committee members who have contributed their best effort to make this event today an outstanding one. So I thank you a lot. And I also would like to thank our co-organizing partner, University Kuala Lumpur, Malaysia Institute of Technology, for their contribution towards this event today as well. Last but not least, I also would like to thank you all, the participants who have supported us, the conference, throughout the years. So this is the 7th edition, so meaning that we have been doing this for almost 15 years. So we thank you because there are also comebacks, regular participants here today. So, and make it Aerotech like a premier aerospace conference in Malaysia. Okay, ladies and gentlemen, Aerotech conference is organized to be a platform for academia, government agency, and also industries to come together and share the current states of aerospace technology, expand our professional networking, and potential collaboration for technology advancement. For this edition, we have selected the theme Sustainability in Aerospace, Engineering and Technology. So whether we realize it or not, aerospace industry has a long and storied history of innovating to meet the societal needs. So in this age where sustainability and environmental friendly solutions and processes have become the key motivators, so it is fittingly for aerospace researchers and development to drive the creativity and advancement of engineering and technology to meet the present and future needs while still also maintain the spirit of sustainable solutions. So we have received close to 70 papers. So after the peer review process, 60 has been accepted, almost 60 has been accepted to the conference, and most of them are going to be presented today. So in times when people are focusing on high impact publications and income generation, so let's not forget that conference like this is where the discussions and the seeds of new ideas actually starts, and new collaboration and also networking are being forged, and also where the knowledge is shared firsthand, face to face. So after all, knowledge without sharing has no value at all. So ladies and gentlemen, so we have prepared a great and interesting program for this today event. So I hope all of you will have an enjoyable and meaningful time at this conference. So before I end my speech, I would like to wish all of you a great conference ahead. Thank you and have a nice day.
Thank you very much, Dr. Fairuz Izzuddin Romli, Chairman of Aerotech 7. Ladies and gentlemen, now I would like to invite our guest of honor, the Deputy Vice Chancellor of Industry and Community Relations of University Putrajaya Malaysia, Professor Dr. Engineer Insinyur Djojodihardjo, on stage to give a speech and to appreciate Aerotech 7 2018.
Thank you so much, to Dr. Salahuddin, our MC, has been always our great MC. Professor Noor Kamaria Nordin, the Dean, Faculty of Engineering, University Putra, Malaysia. Dr. Fairuz Izzuddin, the Chair, Aerotech 7, 2018, colleague of mine. And we have Mr. Iqmal, the Deputy Dean, MIAT University, Kuala Lumpur, Malaysia. We have two distinguished keynote speakers, namely Professor Harijono. Welcome back, sir, to Malaysia. He's from Institute for Advancement in Aerospace Science and Technology, Indonesia. We have another guest of honor, Professor Dr. Fard from School of Engineering, RMIT, Australia. Thank you, sir, for being here with us. It has been a pleasure to host you as well. Distinguished guests, speakers, ladies and gentlemen, a very, very good morning to all of you. First of all, I'd like to welcome all of you to the Aerotech 7 2018. Let us give a round of applause, ladies and gentlemen, because I think every one of us are not having a spirit before we start a very good conference. As all of us know, that the theme selected for this particular year, 2018, is sustainability in aerospace technology. Now, aerospace engineering, in fact, aerospace, the field itself is a very unique field. When you talk about sustainability in aerospace engineering or aerospace technology, there's two scopes that we always have to take into consideration. The first is, of course, the intangible benefit and the tangible benefit. Tangible benefit always will be looking at dollars and cents, which is translated to the return of investment. Now, bear in mind, aerospace technology also dwells with intangible benefits that we can derive. Normally we look at the national security, etc., whereby dollars and cents is immaterial, is irrelevant in that equation. Now, whoever has been doing the science behind this particular field or on this field, I think we are actually doing a favor, in fact, to the country and to the development of the nation, not only here in the Malaysia, but also in the region. Now, with that in mind, I'm happy basically aerospace, field has been addressed through this particular conference. Aerotech is a brand. For the past many years, as has been mentioned by the chair himself, about 15 years this brand has been around. Now it has provided us a very good platform for us to deliberate our ideas, new findings, a way forward, networking internationally and also domestically for the past years. It has been a fantastic conference to me, basically looking at the aerospace fraternity, not only limited to the local participants, but also international participants. Therefore, ladies and gentlemen, Aerotech has indeed grown as a regional brand, in fact. Now, my wish is basically to see before 2 decades, it has to be a global brand instead of a regional brand. This is a very strong regional brand, to my opinion. Now, with that, whatever said and done, I think the success of an event, in fact, the success of Aerotech is indeed lies on a great teamwork. University Putra Malaysia have teamed up with MIAT, University Kuala Lumpur, to ensure the success of Aerotech 2018. Let us again give them a round of applause. It's a hard work. As I've always think and I believe, well, quantity, it doesn't matter. Quality matters. 50 to 60 great papers have been accepted at this conference. And I've seen, yesterday I browsed through the website, I saw basically good topics, very recent topics has been addressed, in fact. Now, I would like to congratulate all the participants basically to pick Aerotech as their preferred conference venue to share their ideas. Keep doing so. We need more and more ideas. More importantly, I think the collaborations is what's needed in the field, because the cost of research in this field is indeed high, ladies and gentlemen, as opposed to other fields. Now, with that in mind, I would like to actually also see in coming years, well, as the chairman has also mentioned, this conference is a biennial conference basically. Every 2 years we try to organize this particular conference. Therefore, I would like to see all of you, in fact, again, in coming years, in 2 years' time for sure, in Aerotech 2020. I think it is going to be another big event. So, meanwhile, do enjoy and stay, I would say, entertained with all those selected speakers, selected papers in this event. Finally, ladies and gentlemen, thank you so much again for being here, and I would like to thank again the organizing committee for having me here, well included in the fraternity of aerospace engineering. Finally, it is my pleasure basically to declare the Aerospace 2018 conference officially open, ladies and gentlemen. Enjoy yourself. Keep coming back to Malaysia for those forums. Thank you so much.
Thank you very much, Dr. Professor, Dr. Engineer Senior Harijono Djojodihardjo. Now, distinguished guests, ladies and gentlemen, allow us to show you a short montage made for this conference. Excuse me for that. Okay. You're not required to stand up. Okay. All right, honorable speakers, ladies and gentlemen, the next highlight of the Aerotech 7 conference this morning are the keynote sessions. And our next keynote speech will be delivered by Professor Dr. Harijono Djojodihardjo. A bit biography about Professor Harijono. He is right now the chairman of the board at the Institute for the Advancement of Aerospace Science and Technology, Jakarta, Indonesia, also known as Persada Kriya Reka Dirgantara. He is also an academician at the International Academy of Astronautics, IAA. He has been appointed in academics as professors in Indonesia, Malaysia, Germany, Japan, among others. And his keynote speech today is entitled "The Vision for Solar Radiation, Magnetic and Electric Sailing for Interplanetary Missions." So the stage now invites Professor Dr. Harijono Djojodihardjo on stage to address the first keynote session. Please.
Bismillahirrahmanirrahim. Very good morning, and first I would like to greet our distinguished guest participants here. But first of all, I think the host, University Putrajaya, Malaysia. It's very good. It's a good feeling for me to be here again, extended campus of UPN. So, Professor Dr. Engineer Harijono Djojodihardjo, and I think I would like to greet the Dean of Faculty of Engineering, Professor Dr. Nur Kamaria Nurdin, and I'd like to greet also the Deputy Dean for Academic Technology of University Kuala Lumpur, the Malaysian Institute of Aviation Technology, MIAT, Mr. Muhammad Iqbal bin Muhammad Ali, and I would like to greet our keynote speaker, Professor Dr. Mohammad Fard, and of course to the host, the organizer, my good friend, Dr. Fairuz Izzuddin Romli, and also Dr. Associate Professor Dr. Azmin Shakrin Muhammad Ravi, and also Dr. Emira Junita Abdullah. But I look also in front of me the head of the Department of Aerospace Engineering, my good friend, Associate Professor Dr. Abdurrahim bin Abdalib. So very good morning to you. Assalamualaikum warahmatullahi wabarakatuh. Greetings to you, and it is quite an honor for me to be invited as a keynote speaker in this, I would say, prestigious conference series, in which I've been part of it for several occasions. So the topic that I would like to share with you is something that actually, well, as an aerospace engineer, we always try to look up, to look to the sky, to look to the even beyond. So I think this topic is would be a fascinating one for you too. That is the vision of like solar radiation, solar magnetic, and solar electric. In all, it is said to be the solar sailing for interplanetary missions. For layman, probably, I don't know if the sky is the limit, but it is beyond that. But as we see from day to day, space also promised something that Dr. Renu, Professor Renu also mentioned. It has tangible and intangible. In fact, if you follow like Elon Musk, he just showed that space will give you a good business in the future. I'm not a businessman, but probably this sort of thing will initiate interest among us. Okay, let's proceed. Okay, this is the outline. I may try to touch upon actually the main sense without going through the detail, and the slide may just serve as a guide, as indication whereabout that we like to discuss. So, by way of introduction, people are, how do we go to space, or do we fly? We need some propulsion, and even for our car, we need some propulsion. And formally, people are thinking about those that are expendables. I think probably taken from the earth, like propellant, or for car gasoline. But within this latest years, we are thinking more about sustainability, you see, and with that, how can we get something without really trying to do more exploitation of the resources. And then we see the sun. So this is the motivation why people are looking to that. And then and these are the three that I will talk about. The first one, this one is the solar radiation, or solar photonic, or solar light sail. And the second one is what is called the solar magnetic propulsion, and the third is solar electric. these are recently, very recent, although it bears some history for earlier pioneers. Let me see, look at before. Now, okay. The progress of such concepts and development spurs many interplanetary, and interstellar application missions, as well as engineering implementation challenges in various disciplines, to mention a few, like in the field of materials and structures. So, the objectives that I may like to take from this is review some of the basic principles, because this may lead us to more review of the propulsion and thrust modeling, and comparison of these propulsion capabilities, such as Babcock and their orbital dynamics, and to gain some insights on some further challenges in their implementation. So this is the, before going to that, then we like to see our solar system, what is known as the heliosphere. I'm not looking beyond that, but with that, what sort of resources do we have and how we go about it. So this is some detail, these two, and then this one is how the Earth is influenced by the solar electromagnetic field, and apparently the Earth has what is called a magnetosphere. There are also other magnetospheres in other planets, but we are concentrating now in this topic on the Earth magnetosphere. And the magnetic sailing actually is trying to imitate that sort of behavior. Okay, by this is a spacecraft, so there's an analogous way. And what is important is that there are some properties and represented by these, the typical premise of the solar wind at the distance 1 astronomical unit, that's the distance between the Sun and the Earth. And apparently, like what we expect, something of nature, it is not clearly constant. It fluctuates, and also depends, has different direction and so forth, as obtained from data like even the Voyager, you see, that is also by Helios 1 solar probe. So, this by way of example, I will not go through the detail. And at this time, the table, unfortunately, I cannot make it very clear, although I started to something that is really legible, but it come out not that good. But just to give you some ideas, what we will discuss, like what would we like to see? I think what will be the propulsion mechanism of these three. You see, this one is the solar radiation, this one is the interaction between the magnetic field of the with the solar wind, while this one is the what is called Coulomb drag between also the solar wind, but as far as electrical charges, to the mechanism that's being developed there. And these are the typical illustration. Not too clear, but I will go through this, but at least give you a summary. And then what are the conceptual versions that have been developed? The version, and you see that there are many versions that have been developed. Also these, there are at least three. And here, I think it is dominated more by a gentleman named Jan Boonen from Finland, which developed this very recently in 2004. and these are another like the historical, some history, a brief history, and then later on I will explain also this some example of the trajectory, orbital dynamics, and then what has been developed to see whether it is experiment in the laboratory or some sort of concept of the spacecraft itself. And I would say that for solar sail, the Japanese has been very successful with what's called the Icarus, which has been deployed successfully, while other countries are not that successful. But in the magnetic sailing, nothing has been launched. And as far as e-sail, several initiatives have been taken by Baltic countries, Finland, Estonia, and so forth, and they have launched some CubeSat to initiate to measure something in the real field in space. And these are some of what we do in the lab, trying to make some simulation, and it is done by what is called PIC, particle in cell method, and apparently, well, there are differences, and they are trying to do using some similarity that may be touched upon later on too. Okay, so this is, first I will talk about the solar sailing. The principle is shown here, that's the sun, and there's a mirror, and that mirror, because of the solar light, then it will be reflected, but this brings some momentum, and it will introduce some thrust. And this is an image of the on-ground verification of a conventional solar sail at DLR. Well, this is actually the artist's impression. I could have a better picture because I think Japanese has published many papers on that. So, this is a way of history. The ideas, this may not be all, see, this is some that I have collected. It's due to, I think, the Japanese professors, so like Svante Arrhenius, Friedrich Chandler, I think it's Russian, and Bernal. So this has been attractive and possibly an accomplishment of space propulsion for decades to come. And the main advantage is that it generates thrust without requiring any propeller. And then how to deploy it and so forth. And you know, the Japanese are very good at origami, and that's why their deployment method has been very successful, I guess, although there are many systems too. Now, this is two versions that I've studied it with my students. One is the flat solar sail, like what you have seen before, and the other one, it will appear in the next slide, what is called the solar photonic vehicle. And the principle of the propulsion is summarized here. And this is the second one, what is called solar photonic thruster. It has another mirror, parabolic mirror, to collect more solar energy, and it's being reflected by a collimating mirror, and then there is a controller, so it's more complex. So these two are very interesting. There may be other concepts, but with these two studies, we may get some more impression on the benefits. Now, these are the dynamic analysis, and as a rule, as a baseline, we may like to see what is called the logarithmic spiral trajectories, like shown here, and the equation of motion actually is very basic too. And here we ratio between the solar light thrust and the gravitational potential of, in this case, the Earth or the Sun. Now, these are some of the results of studies to compare which one is better. Is it SPT or FSS? And apparently in this graph that SPT is much better. And another one, this is based on the transfer time equation derived for local spiral trajectory, that and how the force and varies with the what is called lightness number. Okay. This is another study on the trajectory of emission. See how long it will reach from the Earth to Mars. It is like this with certain characteristics. And this is another one of the transfer time, how it varies with the lightness number. So lightness number then depends on the size of the vehicle. And this is another question from Funaki on orbital transfer by solar light to Mercury, and this is to Saturn. Just to give you an impression of how it can be carried out. Now, temporarily, this is the conclusion that the thrust generated by both SPTs and FSS has the same magnetic offset direction, given the assumption that no radiant thrust is lost. So perfect reflection. And solar photon thruster can generate more thrust. Then, but since the thrust is generated by a smaller surface, altitude control and dynamics of an SPT would be simpler compared to FSS. A flat solar sail has the advantage of simplicity, and common problem with SPT is the elevated sail temperature. That is something that has to be taken care of. Just to get some examples of what are the problems ahead that still have to be solved in their implementation. Now, next we go to the magnetic sailing, and the principle of operation of magnetic sail is based on magnetic propulsion due to magnetic flux in the solar wind from the sun on the bow shaft, similar to planetary situation in the spacecraft. The propulsion principle is implemented by placing a large superconducting loop in the solar wind, as will be elaborated later, or planetary stream of ions. The electric current loop that creates magnetic field will deflect the ions and produce a reaction force. Because the super large area covered by the loop, it's an order of kilometers, it can develop a relatively large force for a given mass. The foremost advantage, again, is the production of thrust without using propellant, and with which then doesn't have to be transported to space. And these are, there are three concepts basically. One is the initial one by Zubrin, and then it was improved by Wingley's and group, and later on Funaki in Japan, and with many colleagues. And with the basic principle is shown here. There's a loop that will introduce the sort of magnetosphere, and because of solar wind, then it will develop thrust. Then, how do you generate that? So plasma has to be, it has to be generated by introducing current in the coil. Now, the improvement by Wingley is trying to introduce a plasma which is the generator is installed in the vehicle. So it is. And the third one, I will go to that. Then that plasma has to be inflated. So these are the some of development, but there are others. Okay, this is what I just said just now. Now, okay, this is on the last one by Funaki. So after the magnetic coil is initiated, then it will be inflated, and then this will be expanded. So it's like a bubble that will grow. So with that, it is hoped to gain more thrust, more efficient thrust. This is again another picture of that, starting with plasma injection, and then this empty field, and then later on by inflation. Now these are some of the parameters that are very significant. There is the characteristic length, and that is, it's shown here as the, this is the magnetosphere, and there is the loop by the spacecraft, and this is the length that is typical for the dimension of the relevant dimension of the spacecraft, in which later on we can measure the thrust. And the thrust is S actually is like the area of a circle with that radius L0, and that is derived from the pressure balance in the magnetic field defined in these equations. Now, another important thing that is in this magnetic field is what is called the Larmor radius and skin depth. So these are the two important scaling lengths. Charged particles moving within magnetic field will revolve at what is called the gyro radius or Larmor radius. And the boundary between the solar wind plasma and magnetosphere is called magnetospheric boundary or magnetopause, where induced currents divide the plasma and the magnetic field regions. It is illustrated in these images. Another one, but to show these blue lines here, the same picture there, are the magnetic field distribution, and then how it varies with distance along line A is shown in the diagram. Now, this is some progress that has been carried out by Funaki. It is, Zubrin called it magma sail, and then Wingley called it M2P2, M2P2, and then Funaki called it MPS, that is magnetic plasma sail. And this is by JAXA, it's schematic of the spacecraft, you see, and it's superconducting coil surrounded by cooling plates, and it has some the initial energy came from the solar panel. Okay, and these are some of the differences between the ion engine, solar sail, and magnetoplasma sail. Okay, these are also the effect of the standoff distance L to the thrust, just to give you an idea how it has been developed and what parameters are significant. And these are again some study on the thrust. Now, we did some relevant studies on, and these are the trying to see how the forces and then how it affects the acceleration compared to the altitude using the assumptions. And the acceleration is actually very minuscule, but that's enough for space that doesn't have any drag. This is now study how the diameter of the coil, you see, is very large, influence the time of transfer. And this is another low orbit transfer studies. It's from 7 kilometers to 900,000 kilometers and to 500,000 kilometers using this magnetic sail. It's another result. You get it out, and these are to see the different design with different coil radius, and another one for transfer to Mars and to Venus. This is only by way of example. And again, this is the comparison between the three: the back sail, the solar photonic thruster, and flat solar sails. And of course, then it depends on the size also. This is another study by the group in Japan to see the trajectories of small-scale magnetic sail when the spacecraft escaped from gravitational sphere of the Earth, bound for Jupiter at different initial velocity and different steering angle. I'm sorry, it may not be too clear, but just give you an idea that these parameters really matter in optimizing the trajectory that you wish to achieve. Now, so what we have carried out is some simulation using Funaki Maxwell scheme, and the performance depends on the radius of the coil and the current. Okay, that's right. Now about the E-sail, it depends actually two important things. That is because of the what is called the Coulomb drag, basically Coulomb drag, and it used cables that has been charged to offset the potential. So because of the electromagnetic field, then it will develop thrust. But there are many details, including there should be some certain aspect that has been developed, that is shield, and also how the wire could be could not be subject to the meteoritic shower, you see, and that has been developed in different technology, what is called the Hoyt tether. It's developed by Hoyt and Ford. And now this is an impression of that. So this is the main body, and these are actually the main tether, and these are those that are secondary that are connecting, and this is an impression of the E-sail in space. Okay. So this is the Hoyt tether, like that. This is the basic principle, but this cannot be implemented, so it is developed like so. And the diameter of the wire is very thin, and the width is of the structure is about 2 centimeters of this Hoyt tether. Next, okay, another impression of that, and this gives you some impression of the dimension and what has been done, and then how it is maintained in space. It's maintained by rotating it, so it has a centrifugal force. So now this is another simulation. Okay, okay. This is another simulation, and then another variation, because in Jan Hunen probably he's developed something that is a baseline. Other people like to see what are the other parameters. And these are the equations, you want to go to them, but this shows that simulation differs from the original one that is in red. Okay. So, and this is another study by the group of Jan Hunen, this Bengali from Italy. Okay. So with that, then I think it's very, very potential. So this is actually the overall impression, and I would summarize this one here. So what will be the challenges and the application? So challenges will be the material structure, deployment architecture, in-flight propulsion control, launching configuration, the initial energy requirement and scheme in the vehicle itself. And then, okay, this is another one that has been developed, showing that there are still areas to develop the system further. This is using a rotating magnetic field. And then the interplanetary E-sail uses positive voltages, electron gun rather than plasma generator, and multiple centrifugally stabilized vectors. So, as a conclusion, then the solar photon thrusters can generate more thrust. The most important limitation of the electric sail, it cannot produce thrust in the Earth's magnetosphere. And the electric sail is a promising candidate for extracting momentum from the solar wind. And the other has been very optimistic that the development has no significant, let's say, significant boundaries, except probably time to develop it. And the electric sail does not need any magnetic fields or superconductors, and its power requirements are modest. So these are some of the things that I've been looking into in the solar sailing, and to give you some impression on what are the promise and what are the challenges. So thank you very much.
Thank you very much, Professor Dr. Harijono Djojodihardjo. So he will be here the rest of the conference. I will hope so. Just an additional information about him. He is also currently an adjunct professor in Presiden University, Jababeka, Bekasi, in West Java, Indonesia. So hopefully we can continue the discussion in this conference. Honorable speakers, ladies and gentlemen, the next highlight of the Aerotech 7th conference this morning are the second keynote session. Our next keynote speech will be delivered by Associate Professor Dr. Mohammad Fard from the RMIT University, Australia, with the title Concept Modeling Method by Optimization of Complex Structures. Just a bit of biography of Associate Professor Dr. Mohammad Fard. He leads the Noise and Vibration Laboratory at the School of Engineering, RMIT University. He is mainly involved in teaching, research and professional activities with industry grants, including from Auto CRC, GM Holden, Futurists in Australia, and Nissan and NHK in Japan. He also has developed Human Body Vibration Lab in RMIT, and his research team is collaborating with Tokyo Metropolitan University, Japan, Southampton University, UK, among others. And we welcome Associate Professor Dr. Mohammad Fard on stage to deliver the keynote speech. Please.
Good morning, everyone. Thank you for the presentation. Yes, I just need your help. Everyone, thank you for giving me this chance to share our research topic and also inviting me for this conference. My name is Mohammad Fard. As explained, I'm from Royal Melbourne Institute of Technology, Australia. So, in fact, before coming here, I did not have a clear idea what is the best topic to share with you in this conference. So, because I knew it's aerospace, I tried to choose a topic that is more relevant to aerospace. But in last, I can say, few minutes, I decided to present, add something to my presentation. So first of all, I will share with you a few research topics that we are doing at RMIT University, my team is doing. So I'm sure that, I hope that some of you, how can I say, find it useful. And then I go to the main topic that I promised to present today. So if you can please go to the other. Oh, yeah, yes. So slide, just from beginning, yes. From slide. Just go first one. Yeah, the first page first. This is my research team at RMIT University. Almost all of them are my postgraduate PhD students. So one of the topics, a few topics that we are doing using this vibration simulator is a driving and vibration simulator. Why vibration is important is because vibration is a cause of motion sickness and discomfort. Vibration is a powerful cause of drowsiness, and also it can cause a significant fatigue. And also it is an important indication of the perceived quality of any system, car or aircraft. So the video that you see here is I did it in Japan when I got my PhD in Tohoku University. So it's I think for 2001 or 2.
The students did a live?
Yes, he's in I think in Mitsubishi Motoku. Okay, it's working. This experiment design was to find the direct effects of the vibration on human headache. So it was very tough. I remember I did myself a few weeks to design the experiment. So I had a few months neck pain because of that. But so the 5 effects of these are, I'm browsing the topic, and then I go to the main concept modeling topic that I promised to present today. So one of the topics that we did it, and recently we are doing it, is continuing to do that, is effects of vibration on drowsiness. So we have found that a particular frequency of the vibration we can entrain the brain wave and makes the driver to put driver in the early stage of the sleep. So this is very important, and recently this one, our very recent publication has received very wide international media coverage because of the importance of the particular frequency of the vibration. So we believe this frequency of the vibration must be controlled in the design of vehicle, aircraft. So otherwise, it may cause, how can I say, first of all drowsiness, second also fatigue, because when the pilot or drivers wants to drive in the fatigue-inducing, drowsiness-inducing condition, it develops a significant mental workload. So to do that, for this result, we have done various physiological and dynamics measurements. So as you see, heart rate variability, the driving performance, EEG, and also pressure mapping and monitoring also the transmission of the vibration. So using one of the key indicators are the LF to HF, we call it in the vibration, in the HRV, that can indicate how much mental workload a driver has it. So this is our result. Our result shows that in within 30 minutes of exposing to the vibrations, the driver can go to the drowsiness stage. So, but often, generally, driver is not exposed to only that particular frequency of vibration. So it's, but in some roads, some condition, that can be can happen. So these are the results. So I don't go to detail, but the second topic that we are doing is the sound pattern recognition. So you are maybe familiar with a mobile phone application called Shazam. So that can identify any music running even in the noisy condition. So we are using that method to recognize or to identify the noise inside of the vehicle. So there we have a squeak and rattle noise, but we don't know the source of the squeak and rattle. So first of all, we use same method that Shazam application has used it. We call it audio fingerprinting. According the audio fingerprinting, is what it does is it picks some unique specification of the sound in time and frequency, and then match it to the database. And so same method, when we use it for the audio fingerprinting, use it in this vehicle squeak and rattle noise, the success rate was not very significant. I'm sorry, this background changed to blue. So the success rate was not significant. And then we started using machine learning. So because we believe that in the vehicle noise, we need to match the feature of the sound. So using the machine learning, we choose the male frequency capacitor coefficient. This is 12 coefficients that human can perceive from the sound. So this is used for voice recognition. We use this method to identify sound pattern from the sound from a large database inside that can be collected from a company. So using that, by increasing the data, our success were increasing, But still, this is an ongoing research topic. So we believe that we hope that we can develop a mobile phone application that can be used for the sound pattern recognition. So the application of this also in aerospace, I think, should be somewhere, because it can be used for various quality detection. So this is the result. Another topic that we have is so development of the human vibration model. So most of the model that available for human body are crash model. So that for vibration model, because of complex non-linearity of the human body, it's sometimes challenging. So for this topic we are collaborating with a company in Japan. So to develop a model, we use the geometry of a crash model and then convert it to the vibration model. So and then collected various experiment without foam, experiment with a rigid seat, experiment. So this data we needed for the correlation of the experiment model and experiment. So I can just summarize the result for you. Is our main target was to develop a model of the combined vehicle seat. This also can be used for aircraft. So vehicle seat and human body in frequencies particularly under 60 Hertz. So if you look at the vibration modes that we have got, this is experiment and this is simulation. So the frequency, the 22.3 and 20 Hertz are very similar, other frequency as well, and the mode shapes. So of course we use the Mach value modal assurance criteria to compare exactly the vector of the mode shape. So one more topic also, recently we have completed it, is this is also a method used for assessment of the discomfort. The current ISO standard, but the current ISO standard is the discomfort versus the vibration level is not accurate. So this is already published by many researchers. So our proposed method is multi-point measurements to capture the vibration modes. Why? Because we believe in some frequency of vibration when seat structure going to the vibration, going to the resonance, the center of the seat back, for example, it can be the node of vibration. So not much vibration in the center of seat back, but the other part of the seat exposed to high level of vibration. So improved measurement is a multi-point measurement. As you see, the correlation improved significantly from the current condition. So these are some more results. And now I go to the second PowerPoint to present my concept modeling. So concept modeling method. So because I was working in the CAE department of Nissan for 6 years, Japan. So one of the challenges that we had in the design of the structure, because the vehicle body is very complicated. So when you do the finite element detailed CAE modeling, so the optimization is not easy, and it's not feasible, particularly in the process of the design of vehicle, because now it's a maximum startup projects till in market is a 1 year in the vehicle design. So in 1 year, so designing, optimizing, and also considering cost. So it's almost impossible to do major optimization in the vehicle body. Everything is done as a minor. So the company, so they need a lot of predecessor knowledge, so predecessor models knowledge. For example, if Nissan has this model, if it doesn't have a previous model, it's difficult to, in a short time, to how can I say, come up with a complete new model because of the need to rely on the predecessor. So vehicle body structure, it's in terms of how can I say, mass is it's very important. So we need to find a better method for optimizations of the vehicle body. So in this research, I will present that how we are use the concept modeling method to optimize it. So concept modeling method means, so make it the model simple, optimize it, and then go back to the detailed model. So as I listed here, so let me review a little bit the history of the CAE, or finite element, in the vehicle auto industry. So in the past, maybe 30 years ago, so not much CAE could be done in real how can I say, industry applications. So we had to rely on a lot of physical testing. So time from startup project to market, it was very long in compared to now. But now, because of the this CAE model, so so a lot of optimization can happen. So vehicle mass became significantly lighter than past. So, but this is not enough. So we need further optimization. So this concept modeling, we believe, can be good for such application. So let me show you how difficult it is to develop a CAE model of the vehicle. So this is a real vehicle. So as you see, this part is body in white. It means the main frame of the vehicle. So it has a few thousand only spot weld on the body. So we had to model even this spot weld. We had to model even paint of the car. So and then this is closures. And this is the mass, for example, you have the cable, you have the many, we call it a non-structural mass, a mass that doesn't change the structural stiffness, but it has in the car, we have to model it. And the last one is also you need to model the air inside of car to predict the noise. So such a complicated model, it needs sometimes 20 hours in supercomputer to run it. So that is the complexity. So in the concept modeling method, the BIW is a body in white, we call it. So in the main structure of the body, so we convert this one to the very easy model. So, but yet reliable. So this is called concept model, and then optimize it. So. So how to convert it? So what we do, we convert any major member of the car from the shell model into the 1D model, beam model. So in order to do that, so we have to take each single cross sections information from the structure. So and then develop a beam model with exactly this cross section information. So for example, for such a cross sections, when we convert it, such a member, this is the side seal of the car. After converting, this becomes so the cross section is exactly the original one. So if there are some changes in between, so we have to develop a new cross section only for this area. So the problem starts in the joint because the beam model is a node-to-node one-point connection in the joint. So you need to use different methods. So which depends on the frequency of the analysis. If it is not high frequency, when I say not high frequency, is under 70 hertz, for example, Boolean reduction method is a static reduction method is good method. But if for higher frequency, for accurate analysis, the modal reduction method can be used. So according to modal reduction method, first we calculate each stiffness in all directions, the stiffness matrix of this joint, and then convert it to the matrix information and give it to the software. So then we need to convert the major panel of the car. What major panel means? The major panel is some panels in the car, like the front windshield, has a significant influence on the structural dynamics. So for example here, without windshield, with windshield is a 53 hertz, without windshield is a 43 hertz, the torsion mode of the body in white. So this is a major panel. So we need to, we develop a much coarser elements of finite element model. Why we do that? Because we need to reduce the computational time. So then the developed model, this is the original model, body white, and this is the concept model. So then the concept model must be validated against the developed model. So the best way is this comparison of the structural dynamics. So structural dynamics in vibration mode shapes, resonance frequencies. So for this one is we use, for the mode shapes we use a modal assurance criteria Mach value, and then and frequency response function as well. So this is, for example, one of the mode of the original detail model, and this is the concept model. So as you see, the frequency are very close. So this is another mode, 41 Hertz and 40 Hertz. This is detail model and concept model. This is a front engine compartment lateral bending. And then this is one more, another mode, which is frequency is similar. So, if I list the mode shapes of the concept model, and these are the advanced model, the resonance frequency are very close, and then the Mach value is minimum is 0.7. So its mode shapes are also similar. So for Mach value, we use the standard Mach value calculation method. So and also we compare the frequency response function. So the solid line is the original detail model, and the dashed line is a concept model. So the graphs cannot, how can I say, it's hardly become exactly same, but what is important, we call it correlation. It means any feature of the blue color model, original model, should appear in the concept model, so we can then optimize this and then apply to the original model. So so after that, after developing the model, so we use the standard method to optimize it. So for optimization this is the last part. Optimization is, so this is the good part of concept model. So in concept model, you have for each part one single cross section. So we can optimize this cross section and then apply to the real model. So these cross sections properties, which is the size, became our design variables. And then we use define a cost function, depends on our objective of optimization. And then using design variables, and and also weight constraint, because what is important is we want to reduce the weight. So we can put our target weight as a constraint, and then optimize it. So as you see, this is the optimized model. So the blue one this time is the original concept model. And then the dashed line is this after optimization. So the comparison, you can see that the resonance frequency is significantly improved. So this amount of improvement is very, very challenging in if we want to use the original model. So, and then we even keep the weight, so reduce the weight of the car. So in the auto industry, even 100-gram reduction of the mass of the vehicle is very important. So, so you can see that concept model can be used, but the advantage of concept model is, another advantage is, for example, if you compare the advanced model, detailed model, and the concept model, calculation of time concept model is 17 minutes, but detailed model for this particular function even is 1 hour, but in the reality is much longer. So, and then, sorry, advanced model was 17 hours, the concept model was 1 hour this time. So this is the size of model was 20 gigabyte for the detailed model, but this one was much less. So this allows the optimization of the vehicle body to become more practical. So this is another comparison. And then also, in order to verify it, sometimes we conduct some experiments in our IT university. So these are our experiment setup for modal testing of the vehicle body structures. And so, as you can see, students are conducting measurement and then continue of experiments and conclusion. Thank you very much.
Thank you very much, Associate Professor Dr. Mohammad Fard from RMIT University. So maybe we can spend some time for Q&A. But before that, I just want to share with you. I used to work in School of Aerospace, Mechanical and Manufacturing Engineering in RMIT with Dr. Fard also at that time. And I still remember being one of the guinea pigs, the subjects. You saw the guy on the pictures. So I used to sit on that thing for like 20 minutes because at that time I remember my colleague Dr. Hamza Azizan, he was doing the study of vibration relation with pilot. Is it drowsiness? Yeah. So although what you've seen here is mostly you can see automobiles, cars, but Dr. Fard also, Dr. Amzar as well, has been done some vibration study on pilots as well. So thank you again, Dr. Mohammad Fard. So if there's any questions for the first keynote speech from Professor Harijono on solar sail, electric sail, and magnetosails interplanetary missions, or for this presentation by Dr. Mohammad Fard. So the floor open to questions. We got 2 mics here, and also there's a mic over there if any of the panelists wants to ask questions. Yeah. Oh, okay, sure. You can ask right away. Yeah.
It's fantastic, I think, presentation. Thank you so much. Also, well, mind-boggling in a way, because you got to sit on the vibrator in a way. Yeah. All right. Just because the natural frequency, I think, is something to do with the natural frequency for sure. For you to hit the chord, right? I mean, for you to fall asleep, so to say. Just now we have seen the vibration. Yeah. So when the body is vibrating, practically you need to hit a certain level of hertz practically to go into the regime. And we know that the regime is very, very intermittent. And looking at the dynamics of a vehicle, or even any vehicle for the matter, even aircraft, etc., you need to stay in the regime for a bit of time in order for you to actually experience that drowsiness, so to say. Is it practical, or it is going to be like outlier? It happens maybe in 1,000 cases, it may happen only 1, or it can be predicted systematically. Are we going through the regime every now and then? That's the first thing. Second thing, each one of those, let's say each one of us may have a different frequency. That would be, be very, very challenging for us to practically teach the machine, or in terms of machine learning, it would be very, very, very difficult, very challenging, because every one of us will have a different frequency. So that's how you tackle and how you think that actually to address these kind of 2 issues basically. In terms of concept, I think it's very, very good, very interesting. But then there are hurdles. I think these are the 2 big hurdles that I foresee. Yeah.
Thank you for the good questions. Individual variability certainly is very important factor. So we know some drivers get drowsy very quickly and some drivers do not. What we found is not the resonance frequency or natural frequency of the body is a factor, is a brain wave. So the good thing is all of us, when the brain wave entrained in frequency of 4 to 7 hertz, we get drowsy. So it means the activation of this brain wave. So the brain wave among the individual are same. So there is not very much same, but its variability is much less than the physical one. So so what we found is the relation between the brain wave entrainment and also the frequency of vibration we put. So what we did is when we put the frequency of 4 to 7 hertz, we found in a group of subjects the drowsiness happens. But when we increase the frequency to the 17 to 20 hertz, which is the alert wave of the brain, so the drowsiness has not happened that much. So still, this is ongoing research, so I cannot say detail exactly what will happen. But the first part we just published it. So also Dr. Amza also did his PhDs because the background of this research, several years research has been done, so to reach this point, and also we need to do several years more. So, but the answer, to summarize my answer, is it's a brain wave is a key, and that part we believe must be controlled the vibration which enter in the brain wave in a bad way. I mean drowsy way. So did I answer your question? So because other part I can tell it. So but in the so we believe if we minimize the 4 to 7 hertz vibration in any vehicle, the stressor of the drowsiness will reduce. So we need to minimize that stressor. So, and we believe some vehicles make you drowsy, some vehicles may not or may less make you drowsy. So, but what we notice is the subjects who even do not get drowsy, the mental workload increases. So it's not good to put more mental workload. So I give one example. Yesterday in my discussion with a team in the university, I told, so when, how can I say, a pilot, for example, going with aircraft 1 and aircraft B, aircraft 1 in 5 hours may make the pilot fatigue equal to the 15 hours of another aircraft. So this individual, this stressor, because of the difference of the stressor. So we need more research to understand, but this can.
All right, we take another question from Dr. Muhammad Tamizi.
Yeah, what Prof. Renu mentioned is almost the same question I want to ask, but I'm more pertaining to helicopters. I experienced before flying with pilot as well, and both were gone to sleep until we almost hit against palm tree, and we managed to bring it under control. Now the question is that for helicopter there is call it 1 per ref vibration for every revolution of the rotor blades. Therefore 1 ref. So it's what we're talking about low vibration. You're talking about between 4 to 7 will induce you to sleep. And that reminds me of the cradle when you're a baby.
Yes.
So that's the main thing. I believe all this is more because when you're a baby you've been conditioned, or maybe by nature itself that we get sleepy with it.
Yes.
So that is the danger where people don't realize, because when you fly in helicopter, eventually you fall asleep because of the vibration. Now, with the modern helicopter, we have what call it sort of humps, right? Head condition, and we have gyros, gyro, and what call it the accelerators. So all these things can be used to, in case of any vibration level to that, it can sort of give alarm to the pilot so that it can stay awake. Is that being applied now? Do you think is there any research done on that aspect?
Sorry, a little bit, I didn't understand the exact question.
One says that nowadays helicopter have monitoring unit humps, and they have sensors such as gyro and accelerometer. Right.
And to control, yes.
So in case of situation where you reach a certain level of vibration, vertical vibration, mostly you're talking about vertical vibration.
Yes.
So there be a way you can use stick shaker or something warning,
Okay.
and that will make the pilot awake.
Yes. Okay. The interesting thing is the research shows such vibration, because already in some cars also we have an alarming vibration in the steering systems when the driver gets sleepy. It's the waking of the driver. But the research shows that cannot put you in the alert mode. It just for maximum a minute delay the drowsiness. So once you are drowsy, so the brain wave should alerting condition. There is no other solution, I think. So those are good to warn drivers should stop, not to continue, because there is no way to continue. So I think that I call those systems as a warning system, not as a, but right now we are developing a system that can alert the driver naturally, rather than warn the driver. So it is still far to develop, but how can I say, we believe it is possible.
All right. We'll have one last question from Professor Harijono.
It's a very simple question actually. When I saw your graph that you have optimized, I'm just wondering, optimized in which way? Is it also related to the human or to general behavior of the vehicle?
Yes, that one, in the auto industry, I think in aerospace should be same. There are, how can I say, targets for first minimizing the transmission of vibration to the occupant, and also noise. So therefore the aim is eventually to optimize for the passengers and driver, but to optimize the transmission of the vibrations. For example, vibration from floor, vibration from steering, vibration from seat. So the target is to, once we minimize it, that is the aim. So another target is, so when we design vehicle, it's always good to make it very light, but the resonance frequency as high as possible. The structural resonance frequency.
Does it depend on the number of passengers?
So yes, when we design vehicle, we call it target cascading. It means the design of the vehicle. First of all, the target design developed based on the operational conditions. For example, in aircraft, operational is 200 passengers. But for vehicle, for example, some average operational conditions and also mass of the particular group of people will be driver, because it depends on which market it is going. And then based on that, we develop the sub-target for the structure. And sub-target also has another sub-target when we call it from the full vehicle to trim body to the body in white. So this sub-target then is the target of designer. But to meet this target, it is not easy. So because still you have to do very complicated optimization. So I can say that you are right. So, but in design, we need to consider operational condition and design.
Thank you.
All right, thank you very much, Professor Harijono Djojodihardjo, and also Associate Professor Dr. Mohammad Fard. Unfortunately, after this, we're going to have a morning break, so we can continue our discussion later. So distinguished guests, ladies and gentlemen, the organizer wishes to express our appreciation to Professor Dr. Harijono Djojodihardjo and Associate Professor Dr. Mohammad Fard for being here with us in support of the conference. May I now invite the Chairman of Aerotech 7, Dr. Farouz Izzuddin Romli, and also the Deputy Vice Chancellor of Industry and Community Relations, Dr. Professor Dr. Engineer Renu Djojodihardjo, to come on stage to present a token of appreciation to our keynote speakers. So first, we would like to welcome Professor Dr. Harijono Djojodihardjo. And also, please welcome on stage also Associate Professor Dr. Mohammad Fard from RMIT University, Australia.
Thank you so much.
All right.
Good photo, maybe?
Yes.
Thank you. All right. Come. Thank you so much.
All right, thank you very much to all distinguished speakers. And thank you also Dr. Faris Romli, and also thank you Professor Dr. Rangan. We have come to the end of the opening session for this morning. The technical sessions will start at 11:30 at the respective rooms according to your program tentative. On behalf of the organizing committee, I would like to invite distinguished guests, all participants, to join us for morning tea outside. But before that, I think it's the tradition of every conference in the world that we have to take a picture of everyone together with this as a background. So before we move on to our second breakfast of the morning, I would like to invite everyone to, maybe we can line up in front here, depending on the photographer. Yeah. Okay, and then with that, we would like to thank you, and we wish you to have a pleasant and fruitful conference. My name is Salahuddin Harituddin. Assalamualaikum, and enjoy the conference. So can we have, how do we want to do this, Mr. Photographer? So can we have everyone? I think we should line up in front here so that we can have that as our background.
Yes. Yes. That's right.
All right, I think we'll do it this way. I think the photographer will be on stage, and it'll be, I think we'll sit behind the setting. Yeah, I think that way.
Yeah, facing this way. All right. Take time.
Ni spot paling nampak dah. It's okay, sorry. Asal depan nampak. Z. Masuk je. Tak nak. Last Dr. Zani.